Thank you. Thank you very much, Anthony. I would also like to thank the organizers for giving me the chance to present and at the same time for their huge flexibility for changing the schedule only for me. So I'm really sorry about this. And again, thank you very much. So this talk is about essentially a project that we have been working on last year together with Tim Möbus, who was my previous PhD student, Andreas Bluhm, Tuvia Gefen, Tong, and Albert Werner. And the project was essentially started from the submission of two papers. So one paper was related to one subset of these co-authors, and one other one was related to another one, where in each of those papers we're trying to essentially learn Hamiltonians which model bosonic many-body systems. And we realized that in both of these previous submissions, the techniques were not strong enough to be both widely applicable to a wide range of Hamiltonians, and at the same time for giving the right kind of optimal scalings, in the sense that we'll make more precise later on. And so we started discussing together, and we realized actually that by joining our efforts and using ideas or combining ideas from these two previous papers, we could actually achieve the best of both worlds. So this is what this talk is about now. So before I give you a more rigorous statement of the problem and the result, let me try to motivate this starting from the context of simulation of quantum many-body systems, on which you have seen many talks, and we will see more talks this week. So in that context, you are given some classical description of a quantum Hamiltonian, and the task here is to devise a quantum algorithm that will allow you to generate a quantum state that corresponds to this Hamiltonian. So the quantum state could be a time-evolved state according to Schrödinger evolution. It could be some ground state of the Hamiltonian. It could also be a Gibbs state arising at a certain inverse temperature beta. And you have to find a way to efficiently, in the best case, implement a good enough approximation of this state on your quantum computer. So I would call this kind of problems direct problems, where you start from this classical description of H and you want to prepare this state, the corresponding state. And to this direct problem, there is an inverse version of it, which people refer to as Hamiltonian learning, where instead of being given the classical description of H, you're actually directly given the states. It could be a Gibbs state, it could be a time-evolved state. And what you have to do is to find a good enough estimate of the Hamiltonian that you believe has generated the state. Okay, so in this talk, we will mainly consider or only consider states which have been generated by the Schrödinger evolution associated to H. Okay, so this is kind of a very general experiment that one can devise on the system to estimate H. So you start with a very simple tensor product state, then you perform some hopefully easy quantum channel on the state to prepare the system in some way. Then you query your unknown Hamiltonian evolution up to time t1. Then you perform some other operation. You query H to time t2 and so on and so forth. And at the end of this experiment, you just measure the system to gather some statistics. And you may allow yourself to perform several experiments of this kind until you have enough statistics to estimate H. So here you have to keep track of all the resources that you actually have to use in order to get your learning algorithm to work pretty well. The main resource that we will keep track of in this talk, which is not the only one, but the main one will be the total Hamiltonian evolution time. So how much do we have to query the Hamiltonian up to which times in total over all the experiments in order to get a good enough estimate of H. But you could also keep track of the number of experiments. We will also do this throughout the talk. So how many quantum circuits of this kind do we actually have to implement on our hardware? And per experiment, you may also want to keep track of the total coherent evolution time that you have to query. So this is in this experiment, this will be T1 plus T2 plus T3. And of course, you also should mention something about how hard it is to prepare these intersparsing channels, and what is the classical pre and post processing computational complexity of the task of the algorithm. Okay, so. This task was first considered in the qubit world, or in the discrete or finite dimensional setting, where the kind of Hamiltonians that people wanted to better understand and to learn were, let's say, geometrically local Hamiltonians on an n-qubit system. So by geometrically local here, I'm being a bit vague, but essentially what I mean is that you can decompose this Hamiltonian into the Pauli basis, where you know what the Pauli strings are. So you know which of these EAs actually constitute your Hamiltonian. And what you don't know is what is the coefficient that comes in front of this EA. Okay, so that's the coefficient that you want to learn using your algorithm. And so now the goal is to learn those things, and the figure of merit that we will use is essentially an upper bound on the maximum error that you make into learning any of those coefficients. Okay, so you want the sup norm of lambda a minus your estimator to be below this threshold epsilon. And you want to be able to do this with some success probability that hopefully will be very close to 1. So you want delta here to be very small. Okay. So the question we want to then ask is, what is the optimal resource count that we will need in terms of the parameter of the problems, namely the number of qubits, the number of interactions, which you may already know about beforehand, so that I will assume to be fixed here, the precision that you want to achieve, as well as the error probability delta. Okay. So now within this rigorously defined framework, I would say there are mainly two types of algorithms that people have been considering. The first one, which is often referred to as the standard limited scaling algorithms, which for which I would say the main paper is the one by Daniel and collaborators, achieves a total evolution time of order epsilon to the minus 2. So we'll see that this is actually not optimal later on. But which is still, polynomial scaling with a precision that you're trying to achieve, and at the cost of having this slightly, larger total evolution time. What their algorithm actually achieves is that per experiment, you need to just query h of a relatively short time. So the time you have to query h per experiment will only scale pretty logarithmically with 1 over epsilon. So they managed to achieve this kind of scalings by essentially combining methods coming from finite propagation, information propagation bounds, together with shadow tomography techniques, which allow them to first reshape the Hamiltonian into a Hamiltonian that only evolves on a subsystem of constant size, and then on that subsystem one can learn the parameters efficiently. Okay, so this is one way of doing it. The other way, for which a paper appeared along the same time as this paper by Daniel and co-authors, is achieving a better total evolution time scaling, which is known as the Heisenberg-limited scaling, which is known to be optimal in the sense that it scales now only inverse linearly with your target precision. But this comes at the cost that per experiment, the time that you need to query your Hamiltonian will itself also scale as the inverse of epsilon. So this is going to be a much longer time per experiment you have to query, hoping that you will not get many errors coming from noise. But at this cost, you can get a much better overall scaling of the evolution. I should also mention that both those algorithms are efficient in terms of pre and post processing. I won't further delve into the details of this here, but that's what you get, yes. So now we want to essentially find a way to extend these types of algorithms from many qubits to many modes, so many bosons. So here we replace our finite dimensional local space by square integrable functions over the real line. And those models, or those systems are modeling bosonic systems, and they are best described in terms of the Fock basis. So the Fock basis state S here for me will just be a tensor product state, which essentially encodes the number of bosons is in mode 1, so this would be S1, number of bosons in mode 2 will be S2, and up to number of bosons in mode n for n mode system will be Sn here. And then given this basis on which I can then work, my interactions will be best described as functions of the creation and annihilation of bosons operators. So for a given mode I just remind you of the definition of the creation operator. This is essentially raising the label of your Fock state by a +1. And the dual of it is just the annihilation operator, which essentially encodes the fact that you're losing one photon on mode I. So now out of those operators, you can define the number operator, which essentially just measure the number of modes, the number of bosons in a given mode I. And the total number of bosons will be given by the sum of those ni's. Okay, so then how do we construct the Hamiltonian? Well, let's just for simplicity assume that we are having a system that is lying on some regular lattice. So to each side of the lattice, you associate a single mode. Okay, so this is the first side, so that to the side 1, you associate A1 and A1 star. And you do the same thing for the side 2. And then out of those modes, you can construct interaction terms by simply taking low-degree polynomials, in this case, in A1, A1 star, A2, and A2 star. And out of those interactions, then the Hamiltonian will just be the sum of those, which will itself also be a low-degree polynomial in AI and AI star. Okay, so this is how we want to think of our local Hamiltonians in this bosonic world. And the goal, again, will be to estimate the coefficients of these polynomials to some precision epsilon and with high enough probability. Okay, so this is not merely just an extension of the finite dimensional setting to this CV case. It's actually like encoding interesting physics. The first kind of Hamiltonian that you may think of in this direction is the Bose-Hubbard model, which is the sum of three kind of contributions. So the first one and the second one are quadratic polynomials in AI and AI dagger, where the first one essentially just encodes the hopping of a boson from mod J to mod I. And the last one is the one that is responsible for this Hamiltonian to be actually hard to analyze mathematically, because it depends quartically on quartically on AI and AI dagger. Okay, so this is what makes this Hamiltonian non-Gaussian or non-quadratic, and that also makes it hard to analyze in general. So, however, for these Hamiltonians, this previous paper by our by now collaborators did manage to achieve this Heisenberg-limited scaling. But their method was very much tailored to the fact that the Hamiltonians that they were considering, typically the Bose-Hubbard model, was commuting with the total number operator. So meaning that you actually preserve the number of bosons when you apply this Hamiltonian. Okay. On the other hand, there are some interesting systems which are modeled by Hamiltonians which do not preserve the particle number. And I have, for instance, adding coupling terms of the following kind, which model the couplings between superconducting circuits. And for those Hamiltonians, these methods that they had found in this paper was not clearly extending. On the other hand, in our previous paper, we could show that for those Hamiltonians, we could achieve the standard limited scaling. So this with a scaling of total evolution time of 1 over epsilon squared. But this meant that we could assess a larger class of Hamiltonians, but at the cost of having a slightly worse scaling in the total evolution time. Okay, so the question was kind of obvious now whether we could combine our techniques together with the ones from this previous paper to achieve Heisenberg scaling for low degree polynomials in AI and AI dagger. Okay, so this is setting the scene. And now I would like to give you the idea of how the algorithm that we did find and which does achieve what the goals that we had set for ourselves works. But I will fix just look at the case where the number of modes is just equal to 1. So I have a single mode system, which is modeled by A and A star. And so the Hamiltonian associated to that single mode system is just given as a low degree polynomial in A and A star. And what I want to do is estimate those coefficients lambda here. Okay, so once you look for a second at this Hamiltonian, it quickly becomes obvious that what you would like to use is a coherent state here. So coherent states are very simple Gaussian states, which I was told you can easily prepare on hardware. And they can also be written in terms of their combination in the Fock basis in this way. But the one nice property of about these coherent states is that they turn out to be precisely the eigenstates to the annihilation operator with eigenvalue given by the label alpha, which is just a complex parameter. So now if I use this equation, I can directly get that the average energy in that coherent state is directly given as a polynomial in alpha and the complex conjugate of alpha. So from here, you see that if you were to have access to those expected values, you could just perform some kind of polynomial interpolation in order to get back the coefficients that are laying here. Okay, so then this allows you to reduce the problem of learning lambdas to the problem of learning or to estimating these average over these coherent states. So now how can one do this? Well, the kind of most naive idea would be to simply set an experiment of this kind where you initialize the system in one of those coherent states. Then you evolve according to your unknown Hamiltonian evolution, and then you measure in the coherent state basis, meaning that you're essentially performing what we call a heterodyne measurement. And if you do this, then looking at the square amplitude corresponding to this experiment, you see that to the first order here, you have exactly the kind of overlaps that you would like to estimate. And out of those, there is a simple way to get back these coefficients lambdas. But of course, this kind of Taylor expansion comes with the fact that you have to also control the second order term here. And to make sure that the second order term does not blow up, you need to ensure that the time at which you're doing your experiment is pretty small, typically of the order of the approximation of the precision that you want to achieve, which means that that first order term, you have to actually estimate it to order epsilon squared. Okay, so then if you use standard concentration bound results, you see that the number of experiments you have to set to get to this precision will scale like epsilon to the -4. And so if you multiply this with the time per experiment, you get a total evolution time of epsilon to the -3, okay, which is much larger than what we would like to get. And on top of this here, actually put it under the rug, the fact that you don't actually necessarily know how to control this term here, so this coefficient that comes in the second order. And in practice, it may very well be that this actually blows up. Okay, so if this part here just blows up, then you actually don't even know how to do this. Okay, so let's move a bit away from these problems and try to think a bit about what we would actually like our Hamiltonian to look like. So what would be an actual easy Hamiltonian that would allow us to learn these coefficients? Well, the simplest thing one can think of is a Hamiltonian, which is just a projection onto the coherent state, which comes with which precisely with the average that you want to estimate. Okay, so let's assume for now that we do have some method that perhaps requires using channels in between, so which intersperse your Hamiltonian evolutions, but which would allow you to reshape your Hamiltonian into one of which the dynamics you can actually access. Okay, so if you assume this, then there is a very neat way of getting a very good estimate on this on the phase here on this expected value. And one way that we could do this is by performing the following experiment. So first you append to your CV system some discrete variable system, so some qubit, which you initialize in the plus state. And then you apply some controlled displacement by a parameter of alpha. So this displacement is again just a Gaussian unitary, whose action on the vacuum, so on alpha equals 0, the vacuum state, is to bring it to the coherent state of parameter alpha. So you perform this controlled displacement. Then you query a non-Hamiltonian or reshaped a non-Hamiltonian evolution. Then you perform a controlled displacement by a parameter of -alpha. And in the end, you measure the qubit system in either the party X or the party Y basis. Okay, so if you do this and you gather enough statistics, you can show that you would actually have a good enough estimate on the average of X or Y, and those one you can directly relate to the real and imaginary parts of the following amplitude, which really just arises from the way that we devise this circuit. And this amplitude turns out to be very close to the phase, so this exponential of -I times t times this angle or some angle which is directly related to the expected value of h. Okay, so by how close you are depends on how large alpha is, but if you bring alpha large enough, you see that this error term will be a Gaussianly suppressed almost. Okay, so we can assume that this just is not here, and hence we have access to this phase here. Okay, so then let's see how we can actually get very efficiently access to the phase. And here we actually use a result that already appeared in that previous paper with that previous paper. So let's say that we want to estimate some angle. For us, the angle would be this expected value of h, and assume that of course, we don't know the angle, but we know it lies within some interval, so within -capital theta and plus capital theta. And assume that we do have access to random processes, x of t and y of t, which are with high enough probability going to be roughly close to the cosinus of theta t and the sinus of theta t, which is essentially what we managed to do in the previous slide. Then you can show that you can actually estimate the parameter theta to precision epsilon by just accessing a number of independent samples from those two processes that scales only polylogarithmically with the size of the interval here over the precision that you're trying to achieve, and with by querying the processes at times which themselves scales like 1 over epsilon. So here you see again that this Heisenberg scaling is somewhat appearing from that result. Okay, so I won't tell you about much about how this result actually can be proved. This was from that previous paper, but the essential idea is that you can turn this estimation problem into a sequence of decision problems where you have to essentially at each step decide whether your parameter theta is below a certain threshold or above a smaller one. So step by step, you're essentially decreasing the interval of confidence, or you're increasing your confidence, but decreasing the interval at which you believe that theta actually belongs. Okay, so let's try to use this result for us. So we apply this result blindly. So we choose now our some polar decomposition for our parameter alpha with radius a and angle phi. So using this decomposition, you can rewrite this average of h in alpha as a polynomial in the radius a with coefficients which are directly related to the parameters that we're trying to estimate. So now, essentially, the idea is first to estimate those coefficients. And you can do this by querying or by estimating this polynomial for different values of a, which you have to choose within some interval that is large enough so that your estimation is good enough. But typically, you can achieve epsilon approximation of these parameters using Chebyshev interpolation techniques by essentially just querying an order 1 amount of those polynomials of this value. So a polynomial, order 1 amount of radiuses a here within some interval which is essentially not too small, so that the largest a plus here is large relative to a minus. Okay, so let's say that we want to achieve this. Then to achieve this, we have to first have an epsilon error estimate of the polynomials for given a's. And here we just use the frequency estimation subroutine that I just described in the previous slide. So we will be able to get this epsilon precision by querying this reshaped Hamiltonian to times which, as we saw, scale just as 1 over epsilon. And the number of experiments that we have to perform for this to happen will scale polylogarithmically with the largest radius that we actually have to query a for. Okay, so once we are here, we manage to estimate these polynomials for different a's. We use those to estimate the coefficients here. Then the last step is to realize that those coefficients themselves are actually related to the parameters lambda in the sense that those parameters are Fourier coefficients of those functions of the phase or of the angle phi here. So we directly get an epsilon estimate on epsilon closed estimate on lambda by just Fourier transforming back those functions. Okay, so with this scheme of ideas, we essentially managed to reduce our problem of getting Heisenberg-limited scaling for approximation of or for estimation of these unknown parameters lambda to the problem of how we can reshape the Hamiltonian H into this much simpler form. Again, by answering this question, we will also see how we actually have to pick this interval at which we have to query our coherence states. Okay, so then let's go back to the kind of general way one can think of reshaping Hamiltonians. So in that paper that I briefly mentioned before, in that finite dimensional paper, the idea was essentially to intersperse these unitary evolutions with very simple single qubit random Pauli matrices, which had two effects. The first one was to actually decouple the Hamiltonian into chunks which are supported onto finite size subregions. So this allowed you to actually parallelize your scheme. So by just learning your interaction terms locally on those subsystems. And on top of this, these random Paulis were also being used to further simplify within those small regions to further simplify the Hamiltonian so that you could actually just access directly one coefficient at a time. Okay, so this was kind of the rough idea for how one could reach Heisenberg limited scaling in that setup. But the way that I just mentioned this, I just talked about this, is by simply performing this kind of discrete time. So first, looking at very short time evolutions of the Hamiltonian and plugging in between those queries, this kind of maps that you have to devise yourself into this kind of xenotype of sequence. You can also think of it in a slightly different way, in the sense that you, at the same time at which you are evolving according to your unknown Hamiltonian, you can, with a relative rate of gamma, here just start some dissipation process, which is generated by some Lindbladian L. Okay, so we will use this is L now, or we have to find some generator L that will have the role of, if the rate gamma is large enough, of reshaping H into the one that we want to, the target H tilde. Okay, so the idea or the motivation behind this actually came from the literature on passive quantum error correction with cat-qubit cures. So I just want to mention this briefly here. The idea here is that in the simplest setting, is that you want to encode a qubit into a bosonic system by essentially stabilizing a two-dimensional subspace in your system. And you can do this using dissipation as well. So the simplest setting is where you take the following Lindbladian. So it's made of a single jump operator. In that jump operator, you just take it to be a squared minus alpha squared. And so the subspace that you're fixing, your code space essentially, will be directly related to the kernel of that jump. And in this case, the kernel is very easy to devise. It's just the span of the coherent state alpha and the coherent state minus alpha, just coming from the fact that, again, these coherent states are eigenstates of the annihilation operator. So we want to kind of use similar ideas, which would allow us to project the Hamiltonian into this alpha subspace, and by the same time just simplify it by a bit. So just replacing all the interaction terms by this average of H that we want to estimate. So for this, we abstracted our framework by a little bit, and we considered the framework of what we call adiabatic limits. So this is kind of a continuous time version of Zeno type of Zeno limits, where you're using once again this kind of Lindbladian here to reshape some other Lindbladian that you started with, if you take the rate gamma to be large enough. So more rigorously, the way that this works is you're considering some Lindbladian k plus gamma L, where k may not only be coherent, it could also have some dissipation part. Okay, so the jumps associated to k will be denoted by kj here. And the Lindbladian L has itself some jumps, so the jumps will be denoted by Li. And we will need to make a few assumptions. So the first assumption that we will make is that these Li's, they have finite dimensional kernels. And I will then denote by P the projection onto the intersection of each of those kernels. Okay, so I also denote by P bar the projection to the orthogonal subspace. So this subspace is finite dimensional, this one will be infinite dimensional. And it will also be very useful for me to make use of this unbounded operator, which is just the projection and co-projection of the sum over I of Li star Li into this orthogonal subspace. Okay. So now for this operator gamma, I will assume a few things. First, I will assume that gamma is gapped above its support. So we have some positive constant eta for which this inequality holds. Second, gamma or these Li's have to be strong enough so that they can control the norms of the H, so H acting on some state, Kj and Kj dagger Kj. So by this, I mean that those operators have to be relatively bounded with respect to gamma. And the last condition that we actually need also is that these jumps Kj, they commute with this projection P. Okay? So under these three assumptions, this is the result that we can prove. It may actually have already been known, but we couldn't find it in the literature, so we had to redo it. So the result is the following one. We can show the existence of constants C and C prime, which are strictly positive, which will depend on the constant that arise from this relative boundiness condition as well as on the gap condition for gamma, such that if you start your process in some states which is already supported in this finite dimensional subspace, then the evolution generated by the sum of K and L gets very close to the evolution generated by a reshaped generator K. And by reshaped here, I mean that you are just reshaping H into PHP. So you're projecting H into that finite dimensional subspace. And you do the same thing for the jumps. So for the dissipation part, you also project Kj into PKJ. Okay, so by how well you're actually doing here is dictated by the rate gamma. So the larger the rate, the better the approximation. Okay, so let me give you a very brief idea of how the proof goes. It uses just very simple tricks. So first of all, we use, as it is very standard in this kind of results, a Duhamel identity, which allows us to control the difference between two evolutions in terms of the difference of the generators of those evolutions. Okay, where we bring sorry, I should have mentioned here, for the proof for simplicity, I will assume that L is made of a single jump, and K is just a coherent, so it's just a Hamiltonian H. So by Duhamel, I get, again, the difference of these two generators. Remember that L gamma was just K plus gamma L. And since the state on which I'm applying this L gamma here is itself supported onto the kernel of L just disappears from this difference. So the only thing that remains is the difference, the commutator to the difference between the unshaped, reshaped H and the reshaped H. Okay, so that's the first step. Next, we can easily see that this commutator that appears in that integral can be rewritten as the sum of two contributions, so which I denote by xs and xs star, where xs you can think of as being off-diagonal block. If you just write your operators into the, if you block decompose them into p and 1 minus p, then xs is just one of those off-diagonal blocks in that matrix representation of my operators. And x dagger will be just the other block. And so by doing this, then I can just rewrite in a slightly more compact way what was already above here. So far I haven't done anything new. But now comes the next trick. So now instead of evolving inside the integral with respect to L gamma, let's evolve according to gamma L. Okay, so the dissipation that should be responsible for reshaping my Hamiltonian. And first of all, because X is supporting these off-diagonal blocks, the first thing you can realize is that the generator L itself, when you apply it to X, it's acting on XS as if you were acting with the operator gamma on the left. Okay, so you have this left action of gamma on XS as an effective as an effective action. And which also means that if you take the exponential now of L and you apply it on XS, then it's the same as if you were just applying the exponential of gamma on the left here. Okay. Now, from here, you just use the gap condition on gamma. So we know that gamma is above some positive threshold eta in order to be able to just reintegrate here. And that's the reason why we are getting this 1 over gamma here dependency here. But of course, here what we did was not to control what we are supposed to control, but to control some other term which is where we change the generator. So we have to still account for the error that we make by changing L gamma by gamma L. So this is this last part that we have to still control. And so here what we did was to essentially use Duhamel a second time to control the difference of these exponentials by the generators themselves. And we are getting, if you just do the proof, you see that you will be getting inside of this second integral some commutator of that kind. So H that commutes, the commutator of H with, again, this exponential of gamma times XS. And the idea now is to use the relative boundedness of H with respect to the gamma operator. So hopefully from here, you're more or less convinced that what you would end up having to control is an operator of this form. Okay, so where you just essentially replace H by gamma here, up to details, and that one you can still control. Although gamma was bounded, now because we have this exponential of minus gamma, and gamma is assumed to be gapped, that product now becomes bounded. Okay, and so you can actually control this by 1 over gamma, but since we have two integrals, we also have a linear dependency on time that comes up within the bound. Okay, so then the results essentially just stands by summing up these two contributions. Okay, so now let's just try to use this result in our one-mode system. So I remind you of the Hamiltonian that we're trying to estimate. This has the following polynomial form. And the jumps that we will choose, or the dissipation that we will choose, will be made of two contributions. One jump, which we take to be the following one. So you take a to some power of r, where r is just an exponent that scales like the degree of h, essentially, times a minus alpha. So this is the first jump. And the reason why we have to use this first jump is to ensure that h is relatively bounded to this gamma operator, okay, where gamma was essentially L squared. So this is why we need to have a strong enough exponent here in order to control the exponents arising from h. Okay, so this is making sure of that I think the second condition of our adiabatic limit result is satisfied. But by doing this, then we are actually ending up having a kernel that is actually quite large, right? Because the larger r, the larger the kernel of your Lindbladian. So to ensure that the kernel remains two-dimensional, we add to this first dissipation term some other term, which is exactly of the same form. You just have to replace r by 1. Okay, so you have a times a minus alpha. And by doing so, then you ensure that the kernel of, or the intersection of the kernels of these two jump operators turns out to be just the span of the vacuum state and the coherent state alpha, right? The vacuum state because you have an a here, and the coherent state alpha because you have a minus alpha, okay? So now the projection onto the subspace, you can ensure to be extremely close to the sum of the projection onto the vacuum plus the projection onto alpha, as long as you take alpha to be large enough, because in that case, the overlap between the vacuum and alpha is Gaussianly suppressed in alpha. And so if you use now this approximation of the projection, our effective Hamiltonian, you can just compute it, and you will see that it turns out to be exactly the reshaped Hamiltonian that we wanted to end up with. Okay, so again, this will be this approximation will be decent if you take alpha to be large enough, essentially of the order of the log of the time at which you want your experiment to be performed. Okay, so now once we are at this step, we can just use frequency estimation, as we've seen before, to learn these parameters. So for this, we need the total evolution time as well as the time per experiment to scale like 1 over epsilon. The number of experiments will scale like the polylog logarithmically with the strength of these coherent labels that we need to access. And by what we just seen above, this will scale essentially polylogarithmically with t over epsilon. And then to ensure, lastly but not least, that our adiabatic approximation is good enough, we also need to take this parameter gamma itself to scale with epsilon as a order 2, so it's the inverse of epsilon squared. Okay, so this comes from the fact that from the adiabatic result, we've seen that the bound we were getting was of order t over gamma, and t itself was order 1 over epsilon, which gives us this degree 2 dependency on epsilon. Okay, so this brings me slowly to the end of the talk. So I essentially gave you the idea of how we can learn these coefficients in the single mode setting. But to go from a single mode setting to a multi-mode setting is actually not so difficult. We just have to use a different kind of dissipation. So the idea is as follows. You first want to get rid of a few of the interactions. The idea being that you want to parallelize your learning algorithm. So let's say you just want to learn interaction terms which are associated to these red edges here. So to ensure that this is not going to be messed up with other interaction terms coming from other edges, we will just set those interactions to 0. And to do this, we again use the dissipation by just setting alpha to be equal to 0 here. Okay, so the same dissipation as above, as before, on each side. So you just sum over the sides, and you take those dissipations on sides for which you don't want to learn the interaction that arises from the side. And you can show that using those dissipations, then the projection onto the kernel of essentially a to some power will project the corresponding interaction to 0. Okay, so we're essentially just shutting down for a few interactions by decoupling, by using this decoupling generator. And then what remains to be done is to use the generator we've seen before on the sites for which you actually want to learn your interactions. And this is, again, exactly done as we've seen in the single mode setting. Okay, so by doing this and by being careful with estimates, you can show that you still achieve this Heisenberg-limited scaling of 1 over epsilon. We just have to blow up this by a little bit, just by a polylogarithmic logarithmic function of the number of modes, which just comes from standard union bounds estimates. The one thing that I do want to mention before the end is that once we have more than a single mode, the relative rate at which we have to dissipate, so this parameter gamma here, turns out to also scale with the system size. So not only does it scale with epsilon, but it also scales like the square of the number of modes. And this is somehow, we don't believe this to be optimal. And in fact, we know that from these finite dimensional papers I've briefly mentioned before, this kind of scaling actually does not appear in those papers. And just want to spend 2 minutes explaining why this is the case and why we cannot just redo what's been done in finite dimensions. So the idea in finite dimensions is that essentially you, just like for us, you only need to measure local observables at the output of a given experiment. And because these observables are local, you can somehow just localize your Hamiltonian dynamics. And the error that you make by doing so is not very large. So you can actually control how large this error is. The idea essentially, if you think of this, or if the infinitesimal version of this circuit, what you're essentially doing is to look at the commutator with your local observable, let's say it's supported on some region C, with your global Hamiltonian. So of course, since the observable OC is of constant support, constant size support, this commutator can be just, or is exactly the same as the commutator of OC with the sum of interaction terms whose support intersect the region C. Okay, so this way you essentially just manage to localize your dynamics, and that's the way essentially you manage to get rid of this n-squared dependency. Now, in infinite dimensions and for unbounded generators, of course, this still applies. Terms which are not supported on C will just vanish in this commutator. The issue is that the commutator itself remains an unbounded object. So we don't know how to control this. In finite dimensions, everything is bounded, so we are fine. But in infinite dimensions, we just don't know what to do with these commutators. So it would be really great if someone had a good idea for how to amend this, maybe amend our overall scheme in order to get rid of this system side dependency. But so far, as far as I know, we haven't managed to perform this. So with this, I'm done with my talk, and I thank you for your attention. I'm happy to take any question.